Okay, so there's a couple more problems to have a look at. The first one, find the general solution for this differential equation here, and also the particular solution given these boundary conditions when t equals 0, y equals 3, and the differential dy by dt equals 3, so they're both equal to 3 in this particular question. So here's our differential equation. The first thing to do is write the auxiliary equation, 9m squared minus 24m plus 16 equals 0, and then putting the values in for a, b and c into the quadratic equation, we work it out, and note that we've got the root equal to 0. So this is a case where the root is the same, real and equal, which is the second example we've got, and m turns out to be just 24 over 18, or 4 over 3. So the general solution is y equals at plus b e to the 4 over 3t. Leaving us 4 over 3 is not a bad idea, certainly when you come to putting in the initial conditions, as we'll see, and also as an exact answer. If I turn that into a decimal, it's 1.3 recurring. So now we're given some initial conditions. We know that when the time is 0, y equals 3 and the first differential is 3. So we can put the initials in conditions in initially when t equals 0, y equals 3. So we've got 3 equals b e to the 0, and b is 3. So we're finding this time that it's much easier to solve because when t equals 0, one of the constants, a, disappears, so we've not got to resort to simultaneous equations in this particular case. We can find b directly, very similar to the example we looked at just before the break. And now to differentiate, we've got to use the product rule. This time u equals at plus b, and v equals e to the 4 over 3t. So if we use the product rule, differentiate each one, and we get that the differential dy by dt is u, at plus b, multiplied by the differential of v, which is 4 thirds e to the 4th over 3t, plus v, the differential of u, which is just a. And so that's that. We can tidy up. Often, when you've got e to the exponential functions there, they can come outside the bracket because they don't change. So bringing e to the 4 thirds t outside the bracket, we're left with this. Just check you see the algebra as we're going through this, that's the important thing. And so now we've got the initial condition that when t equals 0, the differential is 3. So that means this disappears because t is 0, and this bit disappears because t is 0. So left with 3 equals 1 times 4 thirds of b plus a. But we know b is 3, so we can then substitute that in and find a equal to minus 1. Again, just I'll pause while you have a look and check that you see the algebra. So we end up with this particular solution here. And if we plot this on autogram, you can see that's what it looks like. So our initial conditions, it starts at 3, and there's an initial velocity, but this time it looks like after 3 seconds, the thing is going to cross back through 0 again and carry on. And if I were to expand this, it might come back slightly, it possibly disappears down. In fact, no, it's not going to oscillate in this case because there's no sine wave in here. Okay, so we've looked at the examples where we've got 2 real solutions. We looked at an example where we've got 1 real solution, the root is 0. That leaves us one more to have a look at, which is when we get a complex root. So I'll stop this video here and then we'll look at that example.